So, here in week 4, lecture 4 again, uh, this is a very rapid, quick pace through general chemistry, but very much one that tries to hit the essentials and the core things that you will want to know, of course, heading into the second semester of this course, which covers even more advanced topics, but of course, which serves as sort of a general chemical literacy, as I like to frame it, for the rest of your studies, whether it is within chemistry or biology or other allied fields. Importantly, today we get to this point where we've built enough intuition, understanding of how individual compounds, whether they are molecular in nature or sort of an ionic crystal, how they are assembled. We understand some about why they exist and why they're stable and why some others might not be. And we move now to consider how do we predict when they are likely to change through a chemical reaction, uh, either one that we might experience or otherwise predict before we run that experiment. As a bit of review, last week we importantly talked about this issue of how do we explain why and predict which atoms, which elements will bond together. How do we know that a certain combination of elements is a reasonable thing that should exist, is something that might be produced in a chemical reaction versus something that we would relegate as being possible but maybe unstable or rare or unlikely to encounter, and maybe not what we would likely produce in a chemical reaction. For that, really, the leading theory, the leading way we understand and predict is through this molecular orbital theory, MO theory, in which we can visually, there's quantitative, numerical, and computational ways to do it, but we can kind of intuitively, qualitatively piece together why, let's say, two oxygen atoms are drawn and bound together. And that really is by considering how their atomic orbitals, the sort of densities of electron probability, how those might overlap and ultimately glue the different nuclei or bond them together. Some rules we have in sort of assembling these MO diagrams, these combinations, come from the idea that we're going to be adding and ultimately subtracting different atomic orbitals, trying to form some more stable configuration. In many cases, we will combine two orbitals together and we'll produce two more orbitals in exchange. Nice conservation of places where electrons can live. And we typically will form a lower, more stable bonding orbital and a higher energy, less stable anti-bonding orbital. Again, a nice conservation energy of those orbitals as well. If we were to take two s orbitals, for example, which are these nice spherical orbitals surrounding our central nucleus, and we were to push those together, we can see that if we were to add them up, they being the same color or same phase of this sort of wave-like nature of an electron, we would get a constructive interference in which those two orbitals would add together, and you would see an accumulation of electron density of orbital in between these nuclei. This sort of larger clustering, larger grouping of electrons between the nuclei is sort of the glue that holds this molecule together. Negatively charged electrons are sort of gluing together, bonding together these two positively charged nuclei. Now, for conservation, of course, that means we must also produce an antibonding orbital, which typically features a node, this sort of gap between electron density, which really signals that there's no electrons to be found there, that there's a gap or a break between these two nuclei. This is sort of how we might begin to destabilize or make certain combinations of molecules not favorable. But it all depends on where these electrons actually are. And in this case, we have, let's say, one electron from each of our s orbitals populating this lone sigma bonding orbital. And so we only get this bonding interaction that holds our molecule together. So this is favorable. We see that the energy of these electrons are now both lower than they were to begin with. So a predictably favorable interaction that would draw A to B. The other way that we can kind of piece together these orbital diagrams is that they're related to how much these waves, how much these orbitals actually overlap with each other. If you push two spheres together, they overlap a little bit sort of on their periphery. But we have different orbital shapes that have different extents to which their shapes overlap with each other. If we were to take our p orbitals, in this case, for example, the two p orbitals, we will see that because there's essentially sort of a nice lobe of the p orbital poking out to the left and right for this particular orbital, we would expect we would get a stronger interaction, more overlap, just because physically these orbitals sort of poke out more along that bond direction. This stronger interaction, more overlap, means our bonding orbital is stabilized, lower in energy, more favorable. And of course, by inference, our anti-bonding one, which features this node, this break, is less favorable, higher in energy. If we were to have these p orbitals that are sort of pointing parallel to each other, we get what we call the pi-type bonding, which doesn't have really great overlap because they're sort of glancing next to each other. And so we do get some stabilization, but not quite as much as when we have these sigma orbitals that point towards the respective nuclei. So with these two rules, we can kind of build some intuition about how any pair of atoms, any set of atomic orbitals might begin to pierce together. We can compare sort of what type of orbital they are. S with S has a particularly favorable interaction, and P with P matters and depends on the direction of those orbitals, whether it's pointing along our X direction or along our Y and Z, sort of orthogonal to each other. The final sort of rule that we have to piece together and build this intuition, very much something that we practiced in the problem set from last week, is that sometimes if we have the same atom on each side of this molecular orbital diagram, let's say 2 oxygen atoms, the orbitals, of course, begin with the same energy, same atom, same element, same orbital energy. But as we combine different elements of different orbital energies, they're going to have some sort of mismatch, some sort of gap between them. As we have a larger gap or mismatch of energies between our orbitals we wish to combine, we're going to have a less favorable interaction, less stabilization, because they're so different in energy that we essentially end up with a sigma bonding orbital that's essentially identical to the lower orbital energy, and an anti-bonding orbital that's essentially identical to the higher energy atomic orbital. In these cases, we still sort of can have a net lowering of energy. This one electron can go down here to the sigma orbital, but not nearly as stabilizing, not nearly as net beneficial as if we have sort of energy matched orbitals, and every orbital gets lower in energy. We can use this sort of logic to begin to assemble very qualitatively. If you advance sort of further in chemistry, you eventually do this computationally with a lot more numbers and a lot more rules to follow. But we can use this to sort of build a logic of how we might combine different atoms, different elements from our periodic table, and predict, does this molecule exist or not? How stable is this interaction? In the case of something like oxygen bonding or interacting with oxygen, we see that all their orbitals, of course, start at the same energy. All the S's are the same, all the P's are the same since they're identical elements. And we see a very classic pattern where our S orbitals combine together to give a bonding and anti-bonding, and our P orbitals combine together to give bonding and anti-bonding, 2 different types due to the 2 different shapes of these types of P orbitals. We fill our electrons. In this case, each oxygen brings 6 electrons to this particular interaction. So we fill up our 6 electrons from the bottom up, filling up some bonding, some anti-bonding orbitals. In the particular case of oxygen, we see that we are able to fill 1, 2, 3, 4 bonding orbitals that have electron density in between our nuclei that form a bond that glues these 2 oxygen atoms together. And we form 2 anti-bonding orbitals, which sort of begin to destabilize and weaken those 4 bonding orbitals. We look at their net effect, and we see that overall, this pair of oxygen atoms has a net 2 bonding orbitals, 4 minus the 2 anti-bonding, which we think of as sort of a double bond. There's sort of 2 sets of electrons that are net gluing these oxygen atoms together. We also notice that because these oxygen atoms are identical to each other, same element, same energy levels, that all of our orbitals are quite symmetrically split between our 2 oxygen atoms. And we think of that the electrons that are shared between these nuclei in these molecular orbitals are shared equally between each other. There is equal amount of electrons on either side of this particular oxygen O2 molecule. And this is what we would classify as a covalent bond, in which we have electrons shared between our two nuclei within this bond. And because they're shared equally, or almost exactly equally, we would call this a nonpolar or pure covalent bond. This reflects the idea that because the electrons are distributed equally, we have no net positive or negative charges. It's sort of a neutrally charged bond, neutrally charged molecule. That story changes, of course, if we have a different set of atoms, in this case, carbon with oxygen now. Because they're different atoms, they're different elements, they have different orbital energies. Oxygen being further to the right than carbon on the periodic table. More protons, those orbitals are pulled lower in energy. In this case, we see that we still get the same type of mixing patterns, S with S, P with P. But because of this orbital energy mismatch, they're not the same energy, the amount of stabilization is quite weak, it's quite minimal compared to oxygen with oxygen. One unique feature that we also see for this molecule of CO, or carbon monoxide, is that the resulting molecular orbitals, particularly this sigma star and this sigma, are very close in energy themselves. And the same way that we can mix atomic orbitals with each other, we can continue to mix molecular orbitals with each other if they are close enough in energy. And so we tend to see what we call sp mixing, where these two orbitals will further mix, producing a new set of stabilized bonding, destabilized antibonding orbitals. With that, we now have a slightly different MO diagram than what we would see with oxygen, a different relative stabilization of these energies. First, we sort of we count and we check that we have our 4 plus 6, 10 electrons between carbon and oxygen. So we fill up 1, 2, 3, 4, 5 orbitals. In this case, we fill up 1, 2, 3, 4 bonding orbitals that have electrons between our two nuclei that hold these two atoms together. But we only fill one antibonding orbital, which sort of weakens those 4 bonding orbitals. Overall, 4 minus 1 gives us a net 3 sort of bonding interactions. So we would call this, in some parlance, a triple bond, 3 sets or 3 pairs of electrons holding carbon to oxygen. Other things we might notice about this particular MO diagram is that while all these orbitals are low in energy, stabilize a favorable interaction, these electron orbitals are not quite evenly shared between our carbon and our oxygen. The net effect we see is that oxygen, being slightly lower in energy, a higher electronegativity, more protons to pull electrons to itself, in the tug of war over the custody of these electrons, the oxygen side of this molecule is going to shift and pull more of the electrons towards itself. The net effect is that these electrons are not going to be shared equally between our carbon and oxygen. They'll be shared unequally in what we would call a polar covalent bond. The way that we may sort of interpret that is that the lower energy, more electronegative oxygen side has more of the electrons on its side, giving us sort of a slightly negative charge, which we represent by this lowercase Greek delta minus, not a full ionic charge, not a full +1, -1, but a slight negative charge, and carbon, of course, will have a slight positive charge due to this shifting and imbalance of electrons. This polar covalent bond is definitely one that you see quite often, since every time you have a pair of unequivalent atoms, or 2 different elements, we are likely to form a polar covalent bond where the electrons are somehow shared unequally. The last instance we commonly see is when we have a huge mismatch in the energies, and effectively the energies are so far apart that we don't get mixing between them. This is really what we see if you were to combine sodium with chlorine. Sodium on the far left of the periodic table in the 3rd period, chlorine in the same period but on the far right side of the periodic table. Very, very different electronegativities, very, very different orbital energies. Chlorine with more protons, much, much lower energy than sodium. In this case, we once again sort of get really no stabilization from mixing S with S and P with P. And for this particular pair of atoms, our resulting molecular orbitals aren't really close enough to further mix, so they kind of stay where they are. Effectively, what you see is that really no stabilization is happening by forming these molecular orbitals. No energy is saved, no stability is gained by sharing electrons between them. And typically what tends to happen is that the only way we can save energy is if this Sol 3s electron is transferred over to these primarily chlorine type orbitals, effectively not sharing but transferring one whole electron from sodium to chlorine. In this case, because the energy mismatch is so large, and effectively our resulting orbitals are essentially just that of chlorine, we will consider that this electron gets fully transferred, giving us a whole +1 charge and a whole -1 charge to this pair of ions. This we would call an ionic bond, in which the energy difference is so large, the electronegativity is so large and different, that not quite sharing, not a covalent bond, but essentially just a transfer to form two new discrete cations and anions. A lot of MO theory is really there to help us rationalize and predict if we see a certain molecule exists, like carbon monoxide, some element from our from our fourth group, with something from our sixth group. If we see carbon monoxide and it exists, we sort of understand that everything in the same group and same column have similar valence electrons. So carbon has the same 2s, S2 and P2 type configuration as silicon, as germanium, as tin, so on and so forth. And sulfur shares very similarities with oxygen. But why don't we see silicon monosulfide or silicon monoxide or carbon monosulfide? Why don't we see every combination of particular elements from our periodic table? A lot of this is definitely something that is hard to predict without knowing a little bit more and without having some guidance. And sort of a sneak preview, or rather sort of a reference of what you are expected to take away from this explanation of why atoms bond with each other is very represented by our problem set from this previous week. So do make sure that you do that. The last two questions or so really deal with how do we use and think about MO theory in a practical way for us going forward. A big highlight and a salient thing to glean from that is that whenever we form interactions between two different atoms, depending on how mismatched their energies are, we typically will form a nonpolar covalent where electrons are shared equally, polar covalent where they're shared but shared unequally, and an ionic bond where they're essentially completely transferred from one to the other to form a cation with a positive charge and an anion with a negative charge. In reality, because these orbital energies sort of exist along a sliding scale, the periodic table spans a whole range of different orbital energies. There aren't sort of hard and fast divisions that are more than just guesswork. It's helpful for us to understand that the different types of atoms will have different types of bonds, which confer different properties, which we will come to in the following weeks. But this is really how we get there, and it really is a judgment call of when do you consider the orbital energies to be so different that you move from a polar covalent to an ionic bond. Practically, most chemists will sort of draw somewhat arbitrary lines in the sand, and you'll get different answers depending on who you talk to. For our purposes, we will sort of draw arbitrary lines by comparing the differences in electronegativity, these values that rank sort of how low the valence orbital energies are, how strongly they pull these electrons in this sort of tug of war. In somewhat arbitrary divisions, in this class will consider that anything that is greater than 1.8 electronegativity units in difference we'll say is so different that's essentially an ionic bond. Anything that's less than 0.4 is close enough to being equal that we'll consider that to be a nonpolar, equally shared covalent bond. And anything in the middle is going to be this polar covalent, shared but unequally, sort of a halfway point between a non-polar covalent and an ionic bond. As you move forward and you take different chemistry classes, these ranges might change, these divisions might change. Different people have different definitions, but generally we try to summarize a lot of the results of MO theory by taking this comparison of electronegativity. Again, practically, MO theory is really helpful if you have the time and the patience, but there's some shortcuts we can take that are true in about maybe 80% of instances. It's not a perfect shortcut. There's some gaps, but we can still sort of use it to make more tractable work than making MO diagrams till we're blue in the face. One observation we have from MO theory is that most happy sets of atoms will try to satisfy what we call the octet rule, which is trying to make sure that every atom has a valence electron set of 8 electrons, which typically refers to one full shell, completely filled s orbitals with 2 electrons, completely filled p orbitals with 6 electrons. We see in the case of sodium and chlorine, to make sodium plus and chloride minus, that effectively by sodium giving up its single sole valence 3s electron, giving that to chloride with its 7 valence electrons, they've essentially satisfied a full shell's worth, where sodium's highest set of electrons now are the 8 electrons in the second shell, and chlorine now has a full set of 8 in the third shell, giving them an electronic configuration identical to one of the noble gases at the end of the periodic table, which of course have sets of 8 valence electrons. This set of rules, this octet rule, which says that atoms will try to become isoelectronic to a particular noble gas, is a generally good prediction, is a generally good way for us to begin to predict which atoms will begin to bond with each other and how. There are many exceptions, ones that we covered last week, and for that reason, is not the only set of rules that we teach, but again, this octet rule can get us to about 80% of the chemistry that we'll do in the rest of our lives. This mostly true octet rule really isn't satisfactory on its own. It doesn't really tell us how these atoms will bond in 3 dimensions. If we just have 2 atoms bonding together, like oxygen bonding with oxygen, there's really only one way in which those 2 can combine. They'll form sort of this pair, this dimer. But as we begin to add more atoms to this molecule, we have many more options. These sort of differences in how the atoms are attached to each other, how these bonds are arranged, is something we looked at last week with these molecular model kits and sort of seeing these structures in 3 dimensions. The way that we sort of get to these structural shapes and ultimately their properties, we looked at this idea of using Lewis structures, applying the octet rule to first figure out and map sort of a skeleton of what's bonded to each other. In a simple abstraction, we can revisit oxygen here, each with their 6 valence electrons. And to satisfy this Lewis structure and the octet rule, they can share a pair of bonded electrons between them, giving each of them essentially a count of 8. This oxygen will have 2, 4, 6, 8 that it considers its own. And the oxygen on the right similarly has a set of 8 that it considers its own. Shared, but still has sort of custody too. And we can use this to predict a lot of things much more rapidly than MO theory, which really, again, gets us about 80% of the way. Nitrogen bonded with nitrogen to satisfy the octet rule should form a triple bond. Chlorine bonded with chlorine should form a single bond. And something like a noble gas like neon with already a set of 8 valence electrons typically will not need to bond to anything since this already satisfies the octet rule on its own. From there, last week, we looked at how do we take these Lewis structures, this sort of skeleton of what's bonded to what, and try to visualize either physically with a model or on a 2.5 sort of dimension representation, visualize these shapes in a 3-dimensional sense using this valence shell electron pair repulsion theory, or VSEPR theory. Ultimately, it specifies that each of the bonds and each of the lone pairs will try to rearrange themselves in 3 dimensions to space these negative charges out as much as possible. We get very characteristic shapes, many things adopting this sort of tetrahedral shape, trying to arrange 4 different things around a central bonded atom. A conclusion from looking at this 3-dimensional structure, which we will pick up in 2 weeks and continue on from there, is to look at not just how individual bonds might be polar or non-polar, having a slightly positive end and a slightly negative end. But each of these polar bonds can add up to make an overall polar molecule, or they can cancel each other out to make a non-polar molecule, which have a bunch of properties that will be important for how we discuss a lot of the phenomena that we see in our everyday lives. Every bond that acts as a dipole, every polar bond is going to consist of a positive end and a negative end, sort of this distribution of electrostatic charges. And while certainly if a molecule only has nonpolar bonds, electrons shared equally all around, we expect that there's going to be no net positive or negative charge anywhere to be found in that molecule. Everything's sort of evenly balanced out bond by bond. But when we have polar bonds, we get sort of a distribution of positive and negative charges. We now sort of have to consider this three-dimensional shape and the results of that. If we have something like oxygen, again, no polar bonds, only non-polar equal sharing of electrons between the two same oxygen atoms. We would predict that this is an overall non-polar molecule. No particular plus or not minus charges found within this structure, which has a lot of effect on its bulk properties. If we were to look at now molecules that are a little more complex in nature, which now contain some set of polar and non-polar bonds, we begin to now have to consider their three-dimensional geometry and the effect of each individual set of plus and minus charges. So, marching through them, taking a look first at the far left, our molecule of CO2, carbon dioxide. The way that we satisfy this Lewis structure is by arranging it as OCO. You're welcome to try to find a Lewis structure that maybe has OOC or some other variation between them, but very much we see either from MO theory or from our Lewis structure is that it arranges itself in this nice convenient line of OCO. Looking at the distribution of charges, this carbon-oxygen bond is going to be a polar bond, a difference of about 1 electronegativity units between carbon and oxygen, so definitely an unequal sharing. Oxygen being more electronegative, further on the right of our periodic table, lower in energy, is going to mean that oxygen is going to have a slight negative charge, while our carbon is going to have a slight positive charge. But because this molecule is quite symmetric, that there is a pair of equivalent negative charges on the outside of this molecule and a positive charge sort of balanced directly in the middle, we see that there's a balance in the canceling out of the positive and negative halves of this molecule. We may also represent the same idea of there being a dipole, a pair of charges, by these arrows. These dipole arrows have a plus at the tail that indicates where the positive side of the bond is, and this arrow always points to where the electrons would like to go, where the negative end of this bond is. And we see now from this representation that each of these pairs of polar bonds point in equal and opposite directions and effectively cancel each other out. Requires us to think a little bit of these as vectors in three-dimensional space. But for the case of carbon dioxide, we would predict that even though that this contains polar bonds, unequal sharing of electrons, the 3D arrangement means that the overall molecule of CO2 has no net positive and negative halves. They is nicely symmetric, giving an overall non-polar molecule that doesn't have this polar behavior. This is different, of course, if we change and substitute different atoms and different elements. In the case of this OCS now, similar structure, similar arrangement as CO2, but now we see that because the difference between carbon and sulfur's electronegativity is very, very small, we effectively have no polar bond between carbon and sulfur. Now we have a disbalance or an unbalance of the polar bonds, and we have an overall net polar molecule with one side, sort of the carbon-sulfur side, being slightly positively charged, and the oxygen side being slightly negatively charged. If we look at something like ammonia, which gets a little more complicated because of this three-dimensional shape, this trigonal pyramidal shape has a positive side with the hydrogen side being slightly positively charged, and a negative side with the nitrogen side being slightly negatively charged. In 3 dimensions, we sort of think of each of these NH bonds sort of pointing up towards the nitrogen, giving an overall polar dipole moment that points up from the hydrogen side to the nitrogen side. Different molecules with different 3D arrangements of their polar bonds are going to either cancel out, such as carbon dioxide does, or add up together, as in the case of ammonia, giving ourselves an overall nonpolar versus polar molecule. Where we'll go from here, and we will resume this in 2 weeks after we deal first with these chemical reactions, is that again, most of chemistry is dealing with very, very simple laws of physics. Positive charges attracted to negative charges. In the same way that negatively charged electrons are attracted to positively charged protons, polar molecules with a positive and negative end will act like a magnet. Magnets which will attract positive ends with the negative ends of other molecules, so on and so forth. So we're going to put this idea and notion on pause for a moment as we sort of deal a little bit with looking at chemical transformations. But we will come back to this idea since the attraction now not just between different atoms within a molecule, positive protons, negative electrons, will extend now to attractions between different molecules, some with positive ends, some with negative ends, some polar, some non-polar. So the bulk of what chemistry tries to get to is the ability to predict either the properties of a compound. If we see sort of a beaker of a clear liquid, what can we expect of it? How do we know whether it's toxic, whether it's going to explode, whether it's going to evaporate quickly, whether it's going to freeze? How do we predict the static properties of a particular substance? But the other sort of big half of it is trying to predict what happens when I combine different compounds or elements together. How do I predict when I might see a chemical change involved with a particular compound? This is ultimately a very, very hard body of work to predict how chemicals will react. I will say that as a chemist who has been doing this for a time counted in decades, that is still very difficult to accurately predict 100% with 100% confidence what exactly will happen when you mix two chemicals together. Much more important, much easier, and sort of the goal for this course and for your chemical literacy is to be able to discern plausible ways that chemicals might react, plausible things or likely things that might be produced in a reaction versus implausible or impossible things. How can we discern what's reasonable versus unreasonable? A lot of this will come down and really reflect in your normal lives, either within chemistry, within science, and without, of trying to assess risk, for example. If I mix two things together, how do I know that they either will or will not explode? Obviously, everything could explode for some reason or another, but I can probably bet if I mix methane, natural gas with oxygen, there's a high probability, a high plausibility that will have a large explosion, a large chemical change. Versus if I mix methane with water, they probably won't have the same type of large explosive chemical change. How do I assess potentials of hazards, the potentials of chemical reactions? A lot of it is going to require us to use a little bit of our look at MO theory, or a little bit of our ability to predict what molecules exist, why they exist, which ones are more stable and more likely than the other. But I do sort of acknowledge, and I sort of see it in your mind that this is going to be the first of a long sort of series of steps in your lives of trying to figure out how to predict what happens in the chemical reaction. The work we do today will be an incomplete but a helpful step towards that direction. Again, trying to figure out what's plausible before we try to worry about the harder task of figuring out what actually happens. An example of that we already know, and something that we can look back in hindsight, of course, is our good friend Henning Brand, the very diligent alchemist who tried to produce gold by boiling down his urine until gold popped out of it. Within our modern lens of chemistry, we know that because your urine doesn't really contain large amounts of a magical stone, he was probably never likely, it was probably impossible for him to discover this magic philosopher's stone of immortality or gold from his urine. We could have predicted more plausibly that he may have discovered phosphorus, since there's a lot of phosphorus element found within our urine, and other elements that we might predict more plausibly coming from this reaction that Henning Brand was trying to attempt. And so, if nothing else, if you're able to leave this course and be able to predict that your urine is not going to make an immortality stone or gold, that sort of I count as a win. Every step beyond that is going to be a feather in your cap. Within the same vein of how we might improve upon alchemy is really this system of trying to standardize how we discuss reactions, how we discuss chemicals, so we can be very precise about our language and always talk about the exact same thing. In many cases, we represent a chemical transformation by writing a chemical equation, ones which we've implicitly been using so far, and ones which you may have used previously in your studies. We write it with a very, very general form that has what we call the reactants on the left, a big old arrow going from left to right, showing us transforming our reactants into products. Above the arrow, we might specify something we would call a catalyst. A key skill, particularly for those of you who are headed into chemistry adjacent fields, is the ability to take how we might more commonly or casually describe a chemical reaction with plain words and sort of more qualitative descriptions and figure out how to translate that into a more precise prescriptive chemical equation. So an example is that you might, of course, implicitly talk about chemical reactions, and you may say that if methane is ignited, it reacts with the oxygen in the air, as any fire does, and it produces carbon dioxide and water. Very classic when you burn things or combust things. Now, this description is a chemical equation in a sense. It's a chemical reaction that tells me what happens to methane, what happens to oxygen, but it's not terribly precise, and there's more information we could glean from it from a chemical standpoint. To translate this into a chemical equation, we would write the chemical formulas of our reactants. In this case, methane, represented by CH4, and oxygen, elemental oxygen, O2 found in the air. This will undergo a chemical reaction, big old arrow going left to right, producing carbon dioxide and water as our two products. Now, in addition to just specifying what's involved in this reaction, the chemical species, we also can add more information that helps provide more details about what's going on. We could also specify a coefficient that tells us how many molecules of each compound is involved in this reaction. It's not just that methane reacts with oxygen, but we know, for reasons we'll get to, that precisely 1 molecule of methane reacts with 2 molecules of oxygen, or in the units of moles, 1 mole of methane reacts with 2 moles of O2 oxygen. What this coefficient tells us, the number of each molecule involved in this reaction, as well as, of course, how much is produced, 1 mole or 1 molecule of CO2 and 2 moles or 2 molecules of water. We could also specify some conditions that make this reaction happen. This delta symbol is a common way that we represent that heat is a catalyst, that a little spark or ignition or flame is required to set this reaction off. Without it, this reaction is very slow. It doesn't happen until we add this catalyst, we add this spark to make it run. We would also specify the phase of each of these reactants and products using a little subscript. A G represents something in the gas phase, an S for something in the solid, L for liquid, and AQ standing for aqueous, meaning something dissolved in water, which we'll come back to more in depth in a few slides. So from our relatively simple verbal or text description, we try to translate this into something that is more chemically precise, that has more information embedded into it, particularly the chemical identity of these reactants and products, how much of each is involved, and what phase and what other things are required to make this reaction occur. Other things that we should be helpful towards this idea of nomenclature, how we refer to how we discuss things. Language is a big part of chemistry. The reactants in this reaction are methane and our oxygen. It's going to be the stuff we start with, the things we mix together. We might say that these are consumed in the reaction. You may also see them called starting reagents. The products, the things that we make in the chemical reaction, sort of the operative verb would be that we are producing these carbon dioxide and water products in this chemical reaction. We may also say that this reaction yields carbon dioxide and H2O, very specific chemical terms. The catalyst, shown here above the arrow, is neither a product nor a reactant. It's not something that is really consumed in this reaction or produced by this reaction. It really is just there to sort of help the reaction go along a little faster, to trigger sort of this reaction to start. This catalyst is a lot more complex than we are covering in this semester. It is something that you'll cover in much more detail in the second semester of this course. But we leave it here as sort of a seeded notion that this is something that is required to make this reaction go and happen in a reasonable time scale. Fortunately, as you experienced last 2 weeks ago, if you let methane sort of mix with oxygen in the air, it doesn't quite ignite. When we initially turned on our Bunsen burners, we had natural gas leak out into the air, and it didn't produce a flame. It didn't start reacting until we added the spark from our striker. This catalyst is the thing that makes the reaction go, and that's probably as much as we'll say about that for now. It's important for us to be able to recognize and distinguish a chemical reaction from maybe a physical reaction. Really, when we say a chemical reaction, we very much precisely mean a reaction in which we change the identity of the compounds involved, and that pretty much always involves us breaking bonds and making new bonds. Looking at our compounds, our reactants, and our products, here shown as their sort of 2.5-dimensional shape to show what bonds are involved, we would take tally and take note that to turn our methane, CH4, into CO2, it requires us to break apart to separate this carbon-hydrogen bond and reshuffle and reform it now with a new set of bonds, a carbon-oxygen bond. Same thing for oxygen, O2, getting rearranged to now bond to carbon and hydrogen, respectively, in carbon dioxide and water. In each of these cases, everything we start with turns into a completely new molecule, new chemical formula, new 3D arrangement of how they're bonded and arranged. Whenever we have a chemical reaction, we have to implicitly recognize that things are going to be changing at this level. Bonds will be breaking and bonds will be making. If we don't have this type of bond breaking and formation, we probably have something more akin to a physical reaction, such as water boiling going from liquid to a gas. Chemical reactions involve changing the identity of these molecules. One of the biggest things that we as chemists deal with, as you've had a sneak preview in the first few weeks of this course, is that chemistry is a very quantitative science, and we care not just that that methane and oxygen react together. We ultimately care how much of each is produced and how much of each are required. Many of our sort of diarist climate change predictions and trying to understand how much CO2 is produced by burning fossil fuels ultimately boils down to this type of stoichiometry. For every molecule of methane that we burn to produce energy, how many molecules of CO2 do we produce in response? It's not a random number, it's not an arbitrary number, it's not a changing number. This ratio, this stoichiometry, tells us every time we burn a molecule of methane, we produce exactly 1 molecule of CO2, no more, no less. It also tells us how much we consume of each reactant. And all of these ultimately obey this conservation of mass, this idea that within this level of chemistry, we aren't really creating or destroying any of the individual atoms or elements. We're really reshuffling what is bonded to what at any given moment in time. And as this screen comes back, the one exception, of course, is nuclear reactions, which will be covered again in the second semester. But in every other instance, we're really just reshuffling which atoms are bonded to which. We're not changing how many of each there are. We begin and end with the same number of carbon atoms, the same number of oxygen, and the same number of hydrogen atoms on each side of our reaction. This idea that our reaction must start and end with the same number of each element we would refer to as balancing a chemical equation. And it's something that is helpful to know how to do from scratch, particularly when we translate our own equation from a more qualitative description. So we'll practice this. We'll look at a chemical reaction, in this case, the biological process of photosynthesis, which you may have come across before. But a chemist-friendly description of photosynthesis says that plants use light to combine CO2 and water, and in turn they produce oxygen and some sort of sugar. To translate now into a chemical equation that tells us more information in this qualitative description, we need to begin parsing out what the different parts of this sentence tell us on a chemical level. This process of photosynthesis uses light. Light isn't a molecule, it's not a compound, it's not something physical, it's not a bit of matter. In this case, light is a catalyst. Light is something that helps this reaction occur, but it's not something that is fundamentally changed as a product or reactant. So we draw a big arrow showing that this reaction occurs, light acting as a catalyst to make this reaction happen. Our two reactants are going to be carbon dioxide, CO2, and water, H2O. We can use some intuition that carbon dioxide at normal temperatures and pressures is going to exist as a gas. Water will exist as a liquid, so a little G and a little L to indicate those phases. At the moment, we don't exactly know how many molecules of CO2 react with how many molecules of water, so we'll put a placeholder, a coefficient A and B, just as a placeholder for now. And interpreting the rest of this reaction, we know that photosynthesis produces oxygen, O2, which is a gas, and some sort of sugar. And sort of a generic formula for a sugar like glucose would be C6H12O6. Aqueous, meaning that it's dissolved in water. Since most plants are a good deal of water, the sugar is sort of built into its tissue and its vasculature. So this is a translation of our chemical description into a chemical equation. The one missing piece is the ratio or stoichiometry in which these molecules react and combine with each other. What are these coefficients, A, B, C, and D? And how do we pick those to satisfy this conservation of mass, beginning and ending with the same number of each element? Again, our process of photosynthesis, any chemical reaction, and particularly biological reactions, don't change carbon into a different element, don't change oxygen into a different element, just reshuffles around these atoms into new structures. So these coefficients have to satisfy however many carbon I begin with must be the same number I end with. Some of this is going to be a guess and check, and you may have to do this iteratively, but we can start with by noticing that our products, particularly the glucose C6H12O6, has 6 carbon atoms on the right side. For those carbon atoms to appear on the right side, they must have been on the left side. And so the only thing with carbon is our carbon dioxide. And so to have 6 that we end up with, we have to start with 6. So try to set our coefficient of C to 1, and we'll try to set our coefficient of A to 6. 6 carbon dioxide turns into the 6 carbons in this molecule of sugar. As a consequence, it means that we also end up with 12 hydrogen on the right, and the only place hydrogen is found in our reactant is in water. So this coefficient B must also be 6, so that we start with 12 hydrogen, we end with 12 hydrogen. With these filled in, we have one coefficient left over, D, how much oxygen we end up with. Here we have to be a little careful because we notice that oxygen appears both in our sugar molecule as well as our O2 molecule, so we have to take that into account. But by doing some quick accounting, we would notice that our reactant should have 6 times 2 plus 6 times 1, or 18 oxygens we start with. We have to end with 18 oxygens. Our molecule of sugar already accounts for 6 of those 18 oxygens. So 12 must be appearing in this molecule of O2, which conveniently sets D to also be 6. So our final equation, now balanced by having the same number of each atom we start and end with in reactants and products, is this particular one that says 6 molecules of CO2 react with 6 molecules of water to produce 1 molecule of sugar and 6 molecules of oxygen. It's always worth double checking to make sure, again, that we started and ended with the same amount. Sometimes the coefficients need to be rebalanced in case it doesn't quite balance quite easily on the first go. But we'll check that we start and end with the same number of each element, since we aren't changing how many carbon, oxygen, hydrogen we have, just rearranging what's bonded to what. Now, in a lot of the chemistry involved here, you'll work towards trying to understand what has happened once you've seen a reaction. In many cases, things like photosynthesis, we sort of know what's the starting material and we know what the ending material. The key thing is the details of how much is involved of each. And so writing the chemical equations are quite easy. The other half of chemistry is trying to predict an unknown reaction in which I know what reactants I'm starting with. How do I predict reasonable, plausible products that I might end with? How will these atoms rearrange themselves? How do I predict which bonds will be broken, which ones will be formed? It is difficult. Fully admit that, something that you will continue to try to refine over the rest of your studies. But chemistry, luckily, is very much based around pattern recognition, that the same types of patterns repeat over and over in chemistry. Similar molecules will react in similar ways to produce similar types of products. And so a lot of this is sort of trying to observe reactions that have happened in the past as a way to predict similar reactions that will happen in the future. Some general rules that we have to help us, some logic we might build into that, are the things that we make, at least in this level of chemistry, are always going to be stable, realistic compounds. We know sugar exists as a thing that is stable and realistic. It's quite common. And so sugar as either a product or reactant, quite reasonable, quite understandable. Something like CH12 or CO6, which you're welcome to sort of try to draw a Lewis structure or assemble an MO diagram that justifies why that might exist. These molecules, while theoretically could exist, are probably going to be very unstable and therefore unlikely compounds. We typically use the periodic table. Again, sort of these are bonding preferences and sort of reaction patterns that helps us to identify more reasonable compounds versus less reasonable compounds. And as we reset this screen for yet another time, we have a couple of tools that we can use. Of course, we can use the position of the periodic table to tell us what type of cation or anion might it form. We can use Lewis structures and Vesper theory to also predict reasonable molecules that might exist, and MO theory to also predict reasonable molecules that might exist. This previous problem set, the one from last week, has you go through how we might think of why carbon monoxide is a reasonable product, very stable and quite commonly found throughout the natural world. But something like silicon monosulfide, SiS, probably doesn't exist very commonly for reasons of stability, and is probably rare, if not unstable, versus something like Promethium-60, which we talked about in our first problem, so it's probably going to be impossible. Both of these two being unlikely products we wouldn't predict to result from a chemical reaction. The other little bit of logic and intuition is that the weaker bonds will tend to break first and will tend to form first. We may refer to these weaker bonds as being more labile, more easily broken, more easily made. And typically we see that ionic bonds are more easily broken than covalent bonds. Ionic bonds can be easily broken by something like water, so quite common. So if we were to look at something like sodium sulfate, Na2SO4, this is a combination between a cation, sodium plus, and a polyatomic anion sulfate, SO42 minus. We would probably predict that the ionic bond between Na plus and sulfate is going to be broken first, more easily broken, more easily made, than the stronger, less labile covalent bond that exists between the sulfur and the oxygen. So not 100% true. Sometimes weird things happen, but it's generally good intuition to look first at the ionic bonds before looking at the covalent bonds. Finally, the most tried and true way is to look at things that are similar in identity as having similar chemical reactions. looking at something like the combination of HCl, hydrogen and chlorine, or hydrochloric acid. When we react it with NaOH, sodium hydroxide, has a reaction and produces sodium chloride and H2O. We'd probably predict that a similar hydrogen and halogen, HBr, hydrogen bromide or hydrobromic acid, being very similar to HCl, chlorine and bromine being the same group, same column, but offset by one row from each other, should have similar reaction patterns, similar reactivity. And so taking this as a template, we would probably predict that the product of this reaction between HBr and NaOH should be NaBr and H2O, just like we saw for the previous reaction. We will build up a large repertoire of these sort of template reaction examples. Getting our first taste of that on Wednesday as we run some of these chemical reactions ourselves. To help augment this sort of repertoire of reactions we've seen before, templates we might follow to predict products in the future. Within this course, we're going to look at three sort of generic classes of chemical reactions. There are far many more than three, but these three are probably some of the most common that you're likely to see, and certainly the ones that appear here in chemistry, but in biology, in environmental science, in geology, so on and so forth. So the first one that we'll typically see a lot of is going to be a precipitation reaction. This is a reaction in which we take two ionic compounds that are dissolved in water. In this case, we'll use a generic notation, a compound AB, cation A, anion B, reacting with CD, another ionic compound. And we'll get a sort of swapping of cations, swapping of anions, ultimately going from two nicely dissolved solutions in a liquid phase to producing a solid product from one of our new combinations of ionic compounds. We may also commonly see an acid-base reaction, which you'll revisit in the second half of this course as well. But for now, we recognize it as being the reaction between an acid, which transfers an H plus cation, a proton essentially, to some sort of base. This being a very common reaction throughout chemistry as well as ubiquitous throughout biology. And then the final sort of general reaction type we'll look at in this course is going to be an oxidation reduction reaction, or a redox reaction. This is in which, rather than breaking bonds and transferring atoms, we quite often are simply transferring electrons alone from one compound to another. In this case, sort of shown generally as transferring an electron from B over to A. Quite often we'll write a chemical equation that sort of shows the net effect, but quite often it's helpful to write two half reactions, which we'll talk about in a couple slides, that show implicitly this electron being transferred from one to the other. These reactions take many different forms, but there are probably some reactions which you may have already seen, depending on what your lives are like. These precipitation reactions are quite common through environmental sciences. Quite a big problem in industrial waste water treatment and sort of city infrastructure is that the different ions dissolved in your drinking water, in your wastewater, in your wash water will combine together, and where previously they began as nice dissolved clear solutions that flowed nicely through pipes, they may combine together in a precipitation reaction. In this case, you see here a cross-section of a large sewer pipe in which we've had precipitate out a mineral. This one mineral particularly is called struvite, which begins to form these solid crystals that eventually will choke off and block a water service line or a sewer line. Again, this precipitation reaction producing a solid product from two dissolved liquid reactants. These acid-base reactions, of course, appear in a lot of places, but really was made the U.S. Not a powerhouse, but quite notable in the world of baking is our invention of baking powder, which combines acids and bases together to produce gas that creates lifting power, in contrast to the more traditional method of using yeast as a biological reaction. And then finally, these oxidation reduction reactions are quite important to a lot of modern technology. Every battery is built around oxidation and reduction reactions, the movement and transfer of electrons. But even things like photographic film reflect going from a cation of silver, Ag plus, to tiny solid particles of pure elemental silver, Ag, no ionic charge, which gives this sort of black, opaque pattern, which is how most photographic film works. So we're going to talk about each of these three reactions in greater detail, how we may use these to predict things. And of course, on Wednesday, we'll be practicing and exploring these reactions ourselves with our own two hands. This precipitation reaction, again, occurs when we mix two different ionic compounds together. These ionic compounds are things that initially begin as dissolved solutions. These ionic compounds begin as what will probably look like clear, homogeneous solutions, dissolved and uniform down to the per atom or per molecule basis. And is really indicative of dissolving these types of ionic compounds in water to form these aqueous phase mixtures, or things, again, dissolved in water. After mixing these solutions, they will combine together. The ionic bonds will be broken, new ones will be made, and will produce a solid product, so-called precipitate. This solid product we often see as sort of either larger crystals of a solid material appearing in our previously clear solution, or as sort of a cloudy sort of suspension or colloid, again suggesting and showing that we've produced a new product, here a different phase, a solid phase product. You may also see this type of precipitation reaction referred to as a double replacement or a metathesis reaction, really reflecting the idea that our two cations, in this case A and C, are going to switch places, changing what they're bonded to. In this case, A now bonded to D and C now bonded to B. The nature of this double replacement nomenclature. An example, quite common one, will be if you take an ionic compound dissolved in water, like table salt, sodium chloride, NaCl. This appears as a clear, colorless liquid. Silver nitrate, Ag+, and our polyatomic anion nitrate, NO3-, another ionic compound which dissolves in water in the aqueous phase and appears as a clear, colorless, very boring solution. When I mix these together, I have a precipitation reaction. The sodium and silver will effectively switch places. Now sodium associated with this nitrate. But more importantly, our silver is now going to be bonded to the chloride, forming solid particles, solid little chunks and crystals of this silver chloride product. Our previously clear solutions are going to appear as a cloudy white, sort of milky mixture, showing the formation of this product and the occurrence of a chemical reaction. Now, a lot of precipitation reactions are built on the idea that we begin with things that are aqueous, dissolved in solution, down to the per atom or per molecule basis, and end with something that is no longer dissolved. We have solid crystals or solid chunks left over within our products. For that, it's helpful for us to be able to predict when will something dissolve in solution, form an aqueous clear solution, versus form a solid precipitate because it does not dissolve in water, is insoluble, or at least minimally soluble. Like everything in chemistry, the rules for predicting solubility, there are more complicated ones out there, but ones that will get us by for, again, 80% of the world, say that if we have an ionic compound that has an alkali metal, so something from our first group, our first column, something like sodium, lithium, potassium, as well as the polyatomic cation ammonia, things with this are going to always be very, very soluble. So something like sodium chloride will be very soluble because of the presence of this sodium cation. Similarly, things with nitrates, NO3-, this polyatomic anion, are nearly always very, very soluble. Several hundreds of grams can be dissolved in a liter of water, which is a large amount of this compound. Things are usually soluble, such as our halogens or halides, chloride, bromide, iodine, are usually soluble. sodium chloride, potassium chloride, usually soluble, with some very, very notable exceptions. Silver chloride, mercury chloride, lead chloride, and their related bromides are all insoluble, will not dissolve in water, will not form this nice clear aqueous solution. So we see in this chemical reaction that if we were to form a silver chloride, it would form a precipitate, form a solid because it's not soluble in water. Sulfates, similarly, mostly soluble, with some notable exceptions of things like barium, mercury again, lead again, will form insoluble precipitates. There are more complicated rules, and of course, this does not cover the full extent of all the different possible chemicals that could or could not be dissolved in water. But there's a lot more prep work to get to that description that will have to wait for your second semester of this course. For now, these ionic solubility rules are good enough to get us through most of the reactions that we will see here, with some modifications here and there. But it gives some intuition, some leaning of when we would predict we would form a nice soluble aqueous solution versus an insoluble precipitate. A helpful thing to keep in mind, again, is what this looks like at an atomistic level. A lot of chemistry, for as much as we try, is very hard to visualize because it's microscopic, and it really falls on us to use our imaginations to draw little cartoons to try to understand what's happening down at the per atom or per molecule level. And if you were to take a very, very powerful microscope and zoom in on a crystal of sodium chloride dissolving into a glass of water, what you would see is that your nice ionic compound, your ionic solid of sodium chloride, this alternating lattice of sodium chloride, once it hits water, all of these ionic bonds begin to break apart. These ionic bonds dissociate, splitting up into individual sodium ions, individual chloride ions, floating freely and independently of each other, giving us ultimately a homogeneous, uniform solution down to the per atom or per molecule basis. These individual cations and anions is really indicative of when we see a solution at this molecular basis. Anytime we might take an ionic compound and we see that dissolves in water, the reason why our solid white crystal sodium chloride turns into a colorless, clear, transparent solution is that our crystal has now broken down into individual atoms, which are very, very hard for us to see. Whenever we have solutions of ionic compounds that dissociate in this way, we have to think of our reaction not occurring between a crystal of sodium chloride, but between a solution of sodium ions and chloride ions floating freely and independently within sort of the same mixture of NaCl and water. Again, this ionic solubility is really based around ionic bonds only. So of course, Na and Cl will break apart and dissociate into their individual cation and anion. But if we're to take polyatomic ions like ammonia plus and sulfate 2 minus, the water is able to break apart the ionic bond, giving us NH4 plus cations and SO4 2 minus anions, but probably not strong enough to break the covalent bonds between N and H and S and O. With this view that our solutions of NaCl and AgNO3, silver nitrate, are really broken down and sort of already split up into the individual cations, individual anions, a better and more representative way to write the previous precipitation reaction would be to reflect that our reactants are individual Na plus, individual chloride minus, that sort of came together as a pair but very quickly split up once they hit water, and individual Ag plus and individual nitrate minus that came together as a pair but split up immediately as they hit water. These 4 ions now combining together to give sodium nitrate, which individually are still very, very soluble. Sodium always soluble, nitrate always soluble. But of course, silver and chloride forming this exception to our ionic solubility, forming a solid product, silver chloride. Now in this particular configuration, we sort of see something quite interesting. We see that in this actual chemical equation, our sodium plus starts as Na plus dissolved in water, individual cation floating around, and at the end of the day ends up and still stays the same as an individual sodium plus cation floating around in water. And I've said that chemical reactions require a change in what things are bonded to, a change in the identity of these reactants into products. And sodium plus and nitrite minus would be what we might call spectator ions, in that they're in the beaker, they're sort of present for the reaction, but they're not involved in the reaction. They don't undergo a chemical change. They are simply watching the reaction occur. Sometimes it's helpful to show these spectator ions to show what was actually mixed from the bottle into the beaker. But more helpfully, we may often write a net ionic equation, which really just shows the things that are changing. In this case, this complicated mix of 4 different ions really boils down to a chloride minus, individually dissolved, reacting with an Ag silver plus, individually dissolved. And once they react together, now form this insoluble silver chloride, giving us this much more brief, much more salient net ionic equation. In this course, you'll see both. You'll see both sort of the full version of this, but we'll also use these net ionic equations to, one, help simplify our discussions, but also highlight the repeating part of these patterns. For the top reaction, whether we had sodium plus or potassium plus, another alkaline metal, whether we had sodium plus or lithium plus, all these spectator ions don't change the actual chemical reaction occurring between silver and chloride. And so this net ionic equation helps us to predict the actual repeating pattern if we're to change our reactants, now in the case of something like potassium chloride instead of sodium chloride. The other really big category of chemical reactions, one that has a lot of import on biological reactions in particular, is that between acids and bases. And we probably have some definition of acids in our minds, but within chemistry, of course, we all need to make sure we're speaking the same language and the same definition of an acid. And from a chemical's perspective, a chemist's perspective, an acid is something that has an H plus cation. This H plus cation sometimes we'll refer to as a proton, since it's a hydrogen atom minus an electron, which is just a P plus proton. Acids are going to be something that when they dissolve in water, the H plus cation dissociates from whatever anion it was bonded to. And this H plus cation gets added to the water molecule to produce what we call the hydronium cation, H3O plus. H2O plus and H plus, or H3O plus. There are many acids out there, some that we've talked about, again, implicitly so far. Something like HCl, we call hydrochloric acid, because it consists of a hydrogen ionically bonded to a chlorine. This hydrogen really exists as an H plus cation that when mixed with water, this H plus can be donated, can be transferred to this water to form H3O plus and chloride minus, new molecules under this chemical transformation. Any acid that has effectively one H plus that it can donate, we call being monoprotic, one proton, one H plus. Things like acetic acid as well are also considered monoprotic acids. In this particular case, this acetic acid only features one ionic bond between this hydrogen and the acetate anion. These other 3 hydrogens are covalently bonded to the carbon, which is something that we saw with our molecular models from the previous week, as well as we would see from Lewis structures and comparing their electronegativities. So anything with a single H plus to give, we refer to as being monoprotic. Other acids might be polyprotic, several ionically bonded hydrogens that they could donate. Things like sulfuric acid have 2, phosphoric acid have 3, so on and so forth. The way that we've just defined an acid, something that donates an H plus, that makes H3O plus, we will refer to as a Bronsted-Lowry acid, a particular definition of how to refer to an acid. There are other acid definitions out there, but for this course and for most of your studies, we'll work with this Bronsted-Lowry definition of an acid as a thing that donates an H plus. Now for every acid, it must react with a base. Bases are a little trickier. We typically define them in one or two different ways. If an acid is the thing that donates an H+, a base is going to be something that accepts an H+ by complement. Something like ammonia, 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 represented by the chemical formula NH3, is a base because when we react with an acid like hydrochloric acid, the H+ that is donated by HCl is accepted or absorbed by this ammonia NH3. This NH3 turns into ammonium NH4+, acting as a base by accepting that particular proton. Sodium hydroxide, another very, very common base, is considered a base because our sodium and our hydroxide polyatomic anion have an ionic bond that can be split apart by water to give us Na+ cations, OH- anions. And this OH-, this hydroxide anion, can accept an H+ from HCl to form, in this case, water, H2O. H+ plus OH- gives us a molecule of water. By this definition, of course, we refer to this as a Bronsted-Lowry base, something that accepts a proton. Bases are a little weird in the fact there's sort of a few different ways we might define them. Anything that also features an ionic bond between a cation and an OH-, a hydroxide anion, that dissociates, we also consider a base for very similar reasons. So something like KOH, potassium hydroxide, splits apart into K+ and OH-, just like NaOH splits up into Na+ and OH-. Magnesium hydroxide similarly produces two OH- by splitting apart this ionic bond, also a base by this definition. And you may see this referred to as a Arrhenius base, or the Arrhenius definition of a base. Chemists will typically use these two definitions interchangeably. You can see they are related. Sodium hydroxide is a base both by the Bronsted-Lowry and Arrhenius definition, but for being exact in our language, we are aware that there are sort of two ways we define an acid and a base. In this case, both the Bronsted-Lowry and Arrhenius base are sort of used interchangeably within this course. Now, as we sort of implicitly seen, most acid-base all acid-base reactions are going to involve this transference of an H+ from our acid to our base, shown here as sort of this generic form of an acid HA and a base B to form a new pair of products. Acid-base reactions can get very, very complicated. And again, there's a whole section in the second half of this course that requires a little more talk about the energy involved in these reactions, but still it helps serve as a useful template for us to be able to recognize patterns of when acids react with bases and what products we would predict from them. We typically see sort of two modes, in this course in particular, we see two modes and two types of products produced by acid-base reactions. Commonly, we might see an acid and base react to produce water as a product. Water being a very stable common molecule is a good product that we'd predict from a reaction. So combining something like HCl, an acid, with NaOH, a base, transfers this H+ to the OH-, giving us H2O as one of our main products, and what's left over is our NaCl, the remaining cation and anion. Again, we always sort of look and double check that these are reasonable, common, stable molecules, and both H2O, water, and NaCl being very common molecules that we see in our everyday lives, as well as would predict so from both our Lewis structures and MO theory. The net ionic equation, the repeating pattern that we see, is really this transference of the H+, in this case from our hydronium ion to our OH-, giving us water as our main product there. Whether it's HCl or HBr or HI, any other type of hydrogen, bromide, chloride type of acid, they all follow the same repeating pattern of an H+ transferred to OH-. The other thing that we might see is when we see CO2 produced as a product. In this case, we may consider a reaction such as between hydrochloric acid, again, an acid transferring an H plus, to a base like sodium bicarbonate, NaHCO3, sodium cation bicarbonate polyatomic anion, HCO3 minus. In this case, H plus is still transferred over, and our H plus combined with HCO3 to give us H2CO3, just as we saw above with H2O. The remaining spectator ions, Na and Cl, we sort of formally write as being together, though they are spectator ions. This reaction by itself doesn't produce CO2 until this H2CO3, called carbonic acid, sort of decomposes in a second reaction to produce water and CO2 gas as a natural spontaneous process. And so as we sort of move through these acid and base reactions, we're going to be looking out for this repeating pattern, this sort of predicted stable products of an acid combining with a base, either producing water or water and CO2 as their main stable likely products. Places that you might see this can be very, very simple, such as we saw with hydrochloric acid and sodium hydroxide, pretty simple acid-base reaction. But these reactions do get more complicated, but still anchor on the same sort of net ionic equation of H plus being transferred from acid to a base. Baking powder, again, sort of the poster child of early 20th century chemical industry, is a combination of a solid acid and a solid base, distinguishing it from baking soda, which is just a base. You probably use nowadays what we call double-acting baking powder, which is a reaction, a particular type of baking powder that produces CO2 through two different reactions under two different conditions. In the first stage, when you sort of dissolve baking powder into your wet muffin batter, for example, that first dissolution, that first mixing and dissolving in water, produces a reaction that creates CO2 that leavens your batter. Once that batter and the products go into the oven at high temperatures, a second reaction is catalyzed, both of them being acid-base reactions, just occurring under different conditions at different temperatures. Looking at those reactions more carefully gives us a much more complicated acid-base reaction from which we can still pull out the same pattern. Our baking powder consists of a calcium phosphate, in this case, calcium phosphate monobasic, that combines with baking soda, NaHCO3. When we mix those together, we get a proton, an H plus transferred from our calcium acid to our sodium bicarbonate, giving us CO2 and water as our primary products. Again, we're seeing the CO2 production happen. As a net ionic equation, this reflects that one of our H pluses from our hydrogen phosphate gets transferred to our bicarbonate anion, giving us our carbonic acid, H2CO3, which then decomposes into CO2 and H2O. Same acid-base reaction we saw on the previous slide, but now with more complicated spectator ions involved and slightly different full equations, but the same net ionic equation, the same essential idea. In the second step of double-acting baking powder, which occurs at high temperature once your muffin batter is in the oven, the product from our first reaction, this calcium hydrogen phosphate dibasic, CaHPO4, further combined with the remaining sodium bicarbonate to give us another acid-base reaction that once again, as a net ionic equation, transfers an H plus to HCO3 minus to give us H2CO3. This carbonic acid then decomposes to give us water and CO2 once more. Both acid-base reactions, both having the same essential net ionic equation of a proton transfer and H plus transfer from acid to base, in this case giving us CO2 as a primary product. The final sort of template, pattern of reaction that we'll look at in this course are these oxidation reduction or redox reactions. These redox reactions, again, are a large class of reactions, all characterized by transferring electrons from one reactant to the other, or several electrons, as we'll see in a few slides. An example might be the reaction that's found within sort of the normal everyday AA, AAA, C batteries that are slowly going out of fashion. But in this case, that battery starts out with a solid piece of zinc metal, very much the same type of zinc metal that we worked with in our first lab, and a copper 2 plus ion. Copper 2 plus doesn't exist on its own. It might be copper nitrate, copper chloride, but the net ionic equation is just a copper 2 plus with some spectator ions involved. In the reaction that runs the battery, that produces electrons, produces current, and produces energy, we have electrons transferred from zinc to copper, and we see that zinc loses 2 electrons to become zinc 2 plus, copper gains 2 electrons to become copper metal with a no net ionic charge. We can still sort of glean that transfer of electrons implicitly, but we will commonly write these redox equations as half reactions to explicitly show which one is giving up an electron, which one is absorbing an electron. In this case, we sort of write a half reaction for each element. In this case, zinc turns into zinc 2 plus by releasing as a product 2 electrons. And copper 2 plus absorbs or takes those 2 electrons and turns back into copper metal, Cu plus, no net ionic charge. Like any chemical equation that must be balanced to make sure that we start and end with the same number of each element, redox equations have one further stipulation that says that we must balance them to make sure that we start and end with the same number of electrons. In the case of silver, for example, which silver plus only requires 1 electron to become neutral pure elemental silver, whereas copper releases 2 electrons to become copper 2 plus, requires us to generate and to produce and absorb the same number of electrons. We don't accumulate any net number of electrons. So to combine these two half reactions has to reflect the fact that for every copper ion that I need to produce, I must have supplied 2 silver plus ions to produce an electron each. 2 parts of silver produce 2 electrons. 1 part of copper absorbs those 2 electrons, so on and so forth. So just like the equation must be balanced in terms of their elements, starting and ending with the same number of each element, we have to have the same number of electrons produced and consumed on each side. Some nomenclature, some naming in terms that you'll see common throughout redox reactions. Try to specify the term for the zinc in this reaction versus the copper. In this particular reaction, we would say that zinc, being the thing that loses electrons, in this case it loses 2 electrons, we would say that zinc is oxidized. By losing electrons, it's oxidized to zinc 2 plus. By complement, copper, by gaining 2 electrons, is going to be reduced to copper 0 or pure copper elemental. A helpful way to sort of intuit it and sort of understand the naming is that the reduced refers to reducing the 2 plus charge to 0. By adding electrons, we sort of lower the ionic charge from 2 plus to 0. Because these always appear in tandem, every time something is reduced, something else is oxidized. Every time something is oxidized, something else is reduced. We would also refer to these different reactants by what they're doing to the other element. We say here that because zinc is being oxidized, it's losing 2 electrons, it is the thing that is giving 2 electrons to copper. Zinc is the thing that is reducing copper, so we would call zinc a reducing agent or a reductant. Zinc is the thing that reduces the other thing, so it's the reducing agent or reductant. We would also call copper the oxidizing agent or oxidant, because copper is the thing that is oxidizing the zinc, it's causing zinc to lose 2 electrons. Every time we have a reductant, we have an oxidant. Every time we have a reducing agent, we have an oxidizing agent. Every time something is being oxidized, something is being reduced. Now, usually we can look at the ionic charge of our reactants and products to identify how many electrons are being transferred from one to the other. But metals and cations are not the only things that get oxidized and reduced. In fact, most biology very subtly is involved in the reduction and oxidation of different molecules to generate electricity to produce things like NADH and NADPH. And if we look back at our combustion reaction of methane being burned in the presence of oxygen to produce CO2 and H2O, even though we don't see any plus or minuses, we don't see any cations or anions, I will claim and I will justify that this combustion reaction is also an oxidation reduction reaction, a redox reaction that involves transferring electrons in addition to breaking and forming bonds. Here's how we think about that. Instead of having formal ionic charges, +2, -2, whatever it is, every atom within a molecule has what we call an oxidation number. This is sort of a placeholder charge that helps us track the gain and loss of electrons because many of these bonds are going to be polar or slightly unequal in sharing, sort of along this spectrum. Not quite ionic, but definitely not completely non-polar. Even without a formal ionic charge, we can still recognize that a pure element like oxygen just bonded to oxygen with a non-polar covalent bond, is going to have pretty equal sharing of those electrons. Neither oxygen is going to carry a positive or negative charge. So we will assign oxygen, indeed any pure element, to have an oxidation number, sort of an imaginary ionic charge of 0. In contrast, ions, of course, have a net gain and loss of electrons and ionic charge, which would be their ionic oxidation number directly. For anything with a polar covalent bond, such as CO2 or H2O, we still recognize that these electrons are shared unequally. Within water, this OH bond is a polar covalent bond, meaning that the oxygen is going to be slightly negative, hydrogen will be slightly positive, as well as with our CO2, our carbon is going to be slightly positive, oxygen slightly negative. This imbalance of electrons is one way that we see the electrons being gained or lost in an oxidation reduction reaction. We don't see formal charges, we don't see formal ions being made, but we still can see and justify the movement of electrons from one molecule to another. And we'll take a look at sort of how we do so with this combustion reaction. So looking at our molecules, our polar covalent bonds, we can assign an oxidation number, which is like an ionic charge, but recognizes that they are still somewhat shared electrons, not fully transferred. Applying our rules, we typically see that oxygen usually has a -2 oxidation number. It's very electronegative, sort of always tries to pull on as 2 extra electrons. And hydrogen, being very low in electronegativity, we usually assign an oxidation number, a formal charge of +1. With that analysis, we can sort of recognize that this carbon, by being bonded to 4 polar covalent hydrogen carbon bonds, this carbon carries an oxidation number effectively of -4. Not a full ionic bond, it's not a -4 anion and +1 cations, but within the sharing of electrons, we consider this to have sort of a -4 oxidation number. This oxygen, being equal, non-polar in nature, has a 0 oxidation number, an even sharing, no net electrons gained or lost. This carbon, now bonded to oxygen, sort of flips around the other way. This carbon has a +4 oxidation number, reflecting that it's bonded to the 2 oxygen atoms, each being more electronegative, holding on to those electrons within that shared polar covalent bond. This water, of course, once again, also implies the fact that we typically consider oxygen within these covalent compounds to carry a -2 oxidation number, sort of an imaginary ionic charge. In this case, now with these oxidation numbers, we can see something more akin to our zinc and copper exchanging electrons. In this case, we see that for methane to turn into CO2, methane starting at -4 oxidation number, going to +4 oxidation number, has to be oxidized, has to lose electrons, has to increase in this oxidation number, while oxygen gas starts at 0 and turns into -2, being reduced in this process. We would say that methane gets oxidized to CO2, oxygen gets reduced to carbon dioxide and water. We would also call methane a reducing agent, as it is a thing that reduces oxygen. And oxygen, quite apt to its name, is an oxidant or an oxidizing agent because it's the thing that oxidizes methane in this particular reaction. We'll see many examples both of metals with explicit ionic charges gaining and losing electrons, but we will also see these types of non-metal interactions that still have exchanges of electrons, still giving us an oxidation-reduction reaction. Now, a lot of what we do with this unit, again, is trying to build a repertoire of reactions we've seen before, trying to establish and recognize patterns as we go through them. We do a bit of it here in lecture. We will do a bit of it in the upcoming problem set, which is not posted this week to give you some headspace to prepare for the badge test. And of course, we will begin to work with these reactions on a more physical and more experiential basis on Wednesday as we run some of these and start to establish our own patterns. To give us some practice, we're going to take a look at an example that combines a lot of different types of behaviors together. In this case, we're going to translate the description and the idea that you probably shouldn't mix oxidizers like bleach, which has the chemical formula sodium hypochlorite. And you shouldn't mix it with other cleaning products, in particular things that contain hydrochloric acid, also called by the more archaic name muriatic acid, which appears in a bunch of drain cleaner products. And we're told that you shouldn't mix these two together because they produce chlorine gas, which is quite toxic and very, very deadly. But what is going on with this reaction? How do we know it actually is a reasonable thing? And how can we learn more about the specifics of it? We want to translate this description again to a chemical equation with more chemical information that gives us more things to deal with. We start simply by the relation that says that we shouldn't mix sodium hypochlorite bleach with drain cleaners, hydrochloric acid, because it produces chlorine gas, which is of course Cl2 in the gas phase. Now, the description that we're given at the beginning just specifies these three materials, two reactants and one product, but we'll probably notice by virtue of our observation of the balanced equation that this does not specify all the components, all the chemicals involved in this reaction. We start with sodium and we start with oxygen and we start with hydrogen, and those have not yet appeared as one of our products. So our plain text description doesn't tell us everything involved in this reaction. We have to fill in the missing pieces based off of a balanced equation. We would interpret that within this compound, we have ions like sodium plus, the polyatomic anion hypochlorite, OCl minus, indicated by the name, and of course this ionic bond between an acid H plus and the chloride anion bonded to it. So we have four ions, two cations, two anions, that would be broken apart and dissociated when dissolved in water. Looking at our reaction, we do start with two chlorines on the left as our reactant. We do end with two chlorines on the right, but we're missing really the remaining NaO and H. How we might combine those, again, sort of builds off of what patterns have we seen before, what are reasonable ways that sodium, oxygen, and hydrogen might combine together. One reasonable prediction is that sodium plus, very happy to exist as sodium plus, often seen as a spectator ion in the reactions we've looked at so far. And a natural way to combine oxygen and hydrogen, the missing pieces of our reaction, is as the hydroxide anion OH-. So reasonable products, things we've seen before, are reasonably good predictions for things we might produce in this reaction. So a reasonable prediction of the missing component of this reaction is that this reaction not only produces chlorine gas, but the remaining ions combine together to produce sodium hydroxide, NaOH. Now looking at our equation, we have a completely balanced equation. We start with one sodium, we end with one sodium. We start with an oxygen, end with an oxygen. We start with two chlorines, end with two chlorine, one hydrogen, end with one hydrogen. So this is a reasonable prediction of what's missing in this reaction. We start with we would predict a reasonable stable compound that we've seen before, sodium hydroxide, and particularly one that's composed of ionic bonds, so something that's easily formed in these reactions. So it's a reasonable prediction. We could simplify this equation a little more by removing our spectator ions. Again, in solution, our Na and OCl will split apart into respective cations and anions, and as will H and Cl. And the only thing that really remains unchanged in this reaction is the Na+. It both begins and ends as Na+. So if we remove it, we can get to our net ionic equation that more appropriately reflects the key chemical change in this reaction of hypochlorite OCl- reacting with HCl to produce chlorine gas and OH-. Another way to double check that this is a reasonable prediction, that this doesn't seem to break any laws as far as we know, is that this equation is not only balanced in the number of each element, but also balanced in charge. We see that we begin the reaction with a net -1 charge, and we end with a net -1 charge here, again, on a different element, on a different part of this equation. So this seems like a reasonable prediction. It's a reasonable way to interpret this reaction. One way that we may be able to predict, again, is it's a reasonable reaction, is if it squares up with the other things told to us by this description. We're told that bleach is an oxidizer, is an oxidant, is an oxidizing agent, and our equation is valid if we see bleach, OCl- this hypochlorite, behave like an oxidant or an oxidizer. So we once again have a situation in which we don't have net ionic charges on everything necessarily, and we have to apply a little bit of formal oxidation numbers to see if there's transference of electrons. Once again, our rules say that oxygen, when combined in a covalent bond, is almost always assigned a -2 oxidation number, more electronegativity than most other things. Looking at our OCl-, that means that to balance this out, that this chlorine must have a +1 oxidation number. -2 from oxygen, +1 from chlorine gives a net -1 charge for this OCl polyatomic anion. H+, of course, is always 1, meaning that the Cl-, this chlorine now attached to hydrogen chloride, is going to be -1. And when they combine together, they have to turn into this chlorine gas, which, of course, as a pure element, has an oxidation number of 0, equally shared between those two chlorine atoms. In this particular reaction, we see that each chlorine, whether it's from hypochlorite or HCl, acts differently, even though they combine to form the same pure element at the end. The chloride or chlorine in OCl goes from a -1 to 0, gets reduced in that process, and the -1 chloride in HCl gets oxidized up to 0 when forming the pure element chlorine. We see that hypochlorite, by getting reduced from +1 to 0, hypochlorite is going to be our oxidizing agent or oxidizer, which matches what we were told about bleach as an oxidizer, oxidizing agent. And HCl, hydrochloric acid, is therefore going to be our reducing agent by inference and by complement. So this is a reasonable prediction for how this reaction proceeds. It matches up with the products that we're told, and we can observe this chlorine gas. And our prediction of NaOH as our missing product is a reasonable one. NaOH exists. We've seen it before in a reaction. It's a reasonable, stable compound. And this reaction, as we've written it, satisfies the other observation of a redox reaction and of hypochlorite, bleach, acting as an oxidizing agent. So there's many ways that we would be able to confirm our suspicions, but it gives us an idea of a plausible result of this reaction. In particular, it highlights the idea that when mixing this bleach with hydrochloric acid, not only do we generate the very, very toxic chlorine gas, but we actually also generate a secondary hazard. We generate sodium hydroxide, a base, which in other terminology is often called caustic lye. Another type of hazard which can be very corrosive and dangerous in its own right. So By filling in sort of the missing gaps, we can sort of predict not just what happens, but potentially what we don't see happening to us yet, other hazards that we might be aware of. Now, the big part of why we spend a lot of time with these chemical equations is not just to predict products and to make sure we're not missing anything, which is important, but really to try to work on a quantitative basis to say not just that methane reacts with oxygen, but how much methane is required to react with oxygen, how much oxygen is consumed by a certain amount of methane. For that, we really need to worry about this age-old chemical conundrum of worrying about trying to count moles, count molecules, but being unable to do so, and instead having to measure something like mass or volume, which is something we can do in lab. As we sort of worked with previously, and we will continue to work on, we really have two very useful conversion factors that are key for us to go between something we measure in lab, such as a mass or a volume, as well as a property, a molar mass, which we compute based off the atomic masses, or a molarity, a concentration, the number of moles per liter of liquid, per liter of water, per liter of our solution. These two conversion factors help us convert between masses we measure, volume we measure, to a mole or atom we can count to see how these molecules might combine together in a chemical reaction. Things that are helpful to be comfortable doing, of which we'll have ample practice throughout both lab and our problem sets, is to use both the molarity as a conversion factor to convert from volume to moles and moles back to volume, as well as to use this molar mass once again to convert between moles and mass and moles. Things we'll review and have more practice with during lab on Wednesday. Overall, any type of calculation we'll do with regard to the chemical reactions really tries to funnel down from something we can measure, again, a volume of something, a mass of something, and convert that into an equivalent number of moles of that substance. Because ultimately what tells us how many moles of our reactant produce how many moles of our product, or vice versa, comes down to this stoichiometric factor, this ratio between molecules of reactant to molecules of product. In each of these cases, they all require a series of conversion factors, and this particular map found within your textbook is a helpful visual guide that all anchors on the idea of using a molar mass, a density, a concentration like molarity to get to moles, from which we can translate from moles of reactant to moles of product, or vice versa, before we then translate it back onto something we might measure, such as mass or volume. This idea of stoichiometry, again, really thinks of it as just a conversion factor, a relationship between the number of moles or number of molecules of each product and reactant. Let's take a look at an example reaction, one in which the ratio of how these things react is quite important for safety and efficiency. You may be familiar with how soap is made. If you've ever had a particular brand of elementary school or high school science outreach, or you've been a bored person on a weekend, you may have undergone the process of saponification to make your own soap. This, of course, is done industrially, so very few of us do it nowadays, but it's important that we do it properly, particularly because we start with a animal fat represented by the molecule stearin. We could also use a vegetable oil or a vegetable fat as well. We mix that with sodium hydroxide, lye, which is quite reactive, is a strong base, and is quite dangerous if we don't mix the appropriate amount of lye with the appropriate amount of animal fat or stearin. The end products, of course, produce glycerol, which is sort of a byproduct, and the main sort of soap molecule being sodium stearate. Now, we can write this as a chemical equation, and of course, this is a very complicated chemical equation for all the reasons to do with very, very large biological molecules, but we can still see a similar type of precipitation reaction in which we start with sort of two liquids, our stearin animal fat and our solution of sodium hydroxide. And combining these two together, we flip around what's bonded to what to produce a solid product, a solid precipitate, in this case, our solid sodium stearate. In this reaction, we're told a stoichiometry, which tells us how many moles or how many molecules of stearin react with how many moles or molecules of sodium hydroxide. And it also tells us for 1 molecule of stearin or animal fat, how many molecules of soap do we produce in this reaction. Every sort of pair gives us a ratio that tells us how much sodium hydroxide do we need to react exactly with our stearin, and how much soap we expect to make in that process. So with this set of chemical equation, the stoichiometric coefficients, we can begin to calculate some things to figure out how do we actually make soap without wasting material, without having dangerous caustic materials left over at the end of this reaction. And here's a few things we might want to calculate. We might first try to figure out how do we make soap, and how much soap can we produce from a certain amount of animal fat. This is something that industrial chemists are very concerned about, to figure out how much product do you make that you can sell from a certain amount of reactants, since you pay for everything in this process. And so you might begin with a notion that if you start with 1 gram of your animal fat stearin, how much soap do you expect to be able to produce? How much soap do you expect to have to sell at the end of the day? For that, we set up a conversion factor equation just as we had before. But now we're aiming and targeting this conversion to get to a mole-to-mole stoichiometric conversion. To go from something we measure, like grams of stearin, we first want to convert that to the equivalent moles of stearin using the molar mass of our stearin molecule, something which I would just look up and double check because of how large it is. Not worth your time adding up all those atomic masses. But by dividing by our molar mass, we can get to units of moles of stearin. That allows us to apply our stoichiometric ratio that says that for every mole of stearin, we produce 3 moles of our soap molecule, sodium stearate. That we can then convert back to a mass of sodium stearate using our molar mass now of our soap molecule. In this way, we can now figure out how many grams of soap we produce per gram of our starting animal fat. Importantly, this ratio isn't the ratio of a mass-to-mass conversion. It's the ratio of a atom-to-atom or molecule-to-molecule or mole-to-mole ratio, requiring us to use these molar mass conversion factors. If you ever have a doubt that you're doing the right thing or you're not sure you set up this equation correctly, I always encourage you to do dimensional analysis to check that your units cancel out. Grams of stearin divided by grams of stearin, moles stearin per mole stearin, mole sodium stearate per mole sodium stearate leaves me with just the unit of grams of sodium stearate. You can also calculate how much glycerol is left over, the secondary product, following the similar path, similar idea. But now, of course, having this ratio instead of 1 to 3 stearin to sodium acetate, sodium stearate, 1 to 1 stearin to glycerol. Overall, you would probably calculate that for your 1 gram of animal fat that you start with and paid money for, you would produce about 1.14 grams of soap, so slightly more soap than you started with, largely because we're adding a little bit of the sodium hydroxide mass to it. Sig figs, always helpful to double check and make sure that you're not overrepresenting or underrepresenting exactly how much more than 1 gram you are producing. Now, in the real world, and the chemical reaction that you'll be doing for most of your academic and careers, it's very unlikely that you'll exactly nail right on the head the exact right ratio of your reactants. It's very, very hard to measure down to the molecule the exact right ratio of 1 stearin to 3 sodium hydroxide. It's a very unreasonable thing. And in most instances in the real world, we're going to mix our starting reagents, or we're going to mix our starting reactants together, and we'll mix them in a skewed ratio off of our exact 1 to 1, or in this case 1 to 3 ratio. In most instances, we're going to mix one that's going to be slightly more than we need, the other slightly less than we need. The one that we have not enough of, slightly less than the ratio would predict, we call the limiting reagent. It's the one that will be used up completely in this reaction, will run out first. The other reactants, anything that's not the limiting reagent, we are going to consider to be in excess. We will have leftover amounts of this molecule, leftover of this reactant. In making soap, if we had to pick which of our reactants we want to be completely used up and which ones we're okay with there being a little left over, we obviously want to make sure that this soap is going to be safe to rub on your hand and to rub on your skin. And animal fat is okay to rub on your skin, is what your skin is made out of. But caustic lye, the sodium hydroxide, is quite corrosive, quite caustic as its name would imply. And we want to guarantee and make sure that all of our sodium hydroxide is used up as our limiting reagent, that we ensure that there will be none of this caustic material left over after the soap is made. We want to make sure that there's excess stearin, a limiting amount of sodium hydroxide. How do we check that? How do we double check that information? In many cases, the way most people will interact with chemistry is that they'll be given a recipe that says mix this amount of this and mix this amount of that and hope and pray for the best. But how can you double check that a recipe for soap, in this case, is safe? That all of the stearin will be, all of the sodium hydroxide will be used up and we'll have excess stearin left over. A sample recipe might be one that tells you to mix 10 grams of stearin with 1 gram of sodium hydroxide. To my eye, they seem like overly round, sort of arbitrary numbers, and so I would want to double check how much of each reactant will be left over at the end of this reaction. For that, I can double check and see if I use up all my stearin, how much sodium hydroxide would that require? If I use up all my sodium hydroxide, how much stearin would that require? For that, I usually want to pick one reactant, somewhat arbitrarily. In this case, I want to know how much sodium hydroxide is left over. And I'll use it as a starting point to sort of guess and check. So let's say I start with my 10 grams of stearin. I want to assume, let's assume all of my stearin gets reacted. Let's assume stearin is my limiting reagent. For that, I can convert my grams of stearin to the equivalent moles of stearin. I know that for every mole of stearin, I require 3 moles of sodium hydroxide to react with. So I'll multiply by this 3-to-1 ratio, and I'll convert that back into grams of sodium hydroxide. And I see from this calculation that my 10 grams of stearin would require 1.35 grams of sodium hydroxide to completely react and get rid of all that stearin. It's quite fortunate and a good recipe that I only have 1 gram of sodium hydroxide. I have less than the amount required to react all of our stearin. With my only 1 gram, all of my sodium hydroxide will be used up, will be guaranteed to be used up in this reaction, making it my limiting reagent. This means I will have excess stearin left over, no sodium hydroxide left over. And this practice in soap making is called superfatting, ensuring that there's excess fat left over, none of the caustic lye left over as a limiting reagent. However, because I only have 1 gram of sodium hydroxide, I'm not going to produce all the soap I could possibly make from 10 grams of stearin. This limiting reagent, this sodium hydroxide, dictates how much of my soap, how much of this reaction occurs. To use up all my 1 gram of sodium hydroxide, once again I use my conversion factor train, and it tells me I only use up 7.43 of my 10 grams of my stearin. I use less than total amount. Some of it will be left over. About 2.7 grams of my stearin are left over. So with this limiting reactant, I will not run this reaction to completion. I will have 1 reactant used up, my sodium hydroxide. 1 will be left over, an insight that I can only glean and calculate based off of these stoichiometric coefficients. So we'll come back to these ideas, and we'll be using this quantitative side of chemical reactions in addition to the qualitative predictive side we began this lecture with, both of which are quite important to how we view the chemical world. These are things, of course, we'll get practice with on Wednesday, as well as next week, as we sort of deal with two variants of chemical reactions. First with precipitation reactions on Wednesday, and then acid-base reactions the week after. We'll end a little early today, partly because we have some things next week. So obviously on Wednesday we have lab as normal. This will be a sort of exploratory lab, so one that's going to be a lot lighter in calculations, a lot less taxing than our first two labs have been, to everyone's delight and relief. Again, sort of giving us first-hand experience, helping us build this catalog of chemical reactions we've seen before that we can use as templates to predict reactions that we might encounter in the future. You're welcome to turn in lab report number 2 today, problem set 3 from last week. You, of course, are not required to turn them in. If you are happy to accept a very small, minor 10% late penalty and hold on to your problem set to spend more time with it. One advantage of turning in your problem sets, even if they are imperfect, is that you get access to the solutions, which sort of give you the way I solve these problems as a helpful way to prepare for our badge test. Again, you'll notice that your final grade is only 10% of which is worth, or problem sets are only worth about 10% of your final grade. So it's not nothing, but it's a relatively small amount of your grade, and it's not there to punish you, but rather to encourage you to try to sort of get your hands wet, but ultimately to try to prioritize moving through the material at a reasonable pace. So you're welcome to turn things into me now. You will get access. You get access to the solutions as soon as you turn them in, and they are graded. But you are welcome to hold on to them if you'd like another swing at it. I will also hang around if there are questions on problem sets or lab reports today as well. There is no problem set this week, mostly because there is a badge test next week, and this badge test will cover everything up through last week's materials, not including what we discussed today. In general, our badge test will be next week, Monday. There'll be an hour review session, about from 9 till about 10, and we will start very promptly at 10 a.m. And you will have the entire remaining lecture time to complete this badge test at your own pace. It's a long window of time and it's there if you need it, but I do not suspect everyone will need all of the time. So I expect that it will probably last less than 4 hours, but you do have 4 hours if you so choose. Now this badge test is potentially something very different than what you've encountered in previous classes. Again, this badge test is trying to give me a way to see if you have mastered very important topics in this level of chemistry. The rate at which you learn material is variable, and I really don't require that you have learned all these things until at latest the very, very last day of class with no penalties. These badge tests are cumulative, meaning that it doesn't matter when you pass and gain a certain badge or pass a certain proficiency badge test. As long as you pass them all by the end of the course, you'll get full credit, full marks for everything. Again, I don't care when you learn things. I just require that you learn them by the end of this particular course. Each badge is testing a particular concept or skill that we've covered in the first 3 lectures of this class. Things dealing with sort of this general issue of math and calculations and chemical nomenclature we talked about in the first week, are very, very high-level view of the structure and behavior of an atom, particularly with a lot of reference to electronic structure and atomic orbitals. And then what we talked about last week, these different ways that we describe why things bond together. Molecular orbital theory being one of them, but our Lewis structures and our look at electronegativity differences being part of the ways we describe these bonds. Each of these 13 skills you will be tested on essentially individually. Each of these 13 skills, each of these 13 badges is going to have maybe a 1 to 2 page short little test. You'll receive a packet of all of them stapled together. Each 1 or 2 pages is a self-contained test that will test you on one of these skills and one of these concepts, very similar to the types of questions, the level of difficulty that you had during the problem set. So they're very helpful ways to prepare for this. each badge is out of 4 points. Out of 2 points, sort of half-point increments within there. And you're welcome to pass as much of that test as you are able to. Obviously, this is iterative, so anything you don't pass here on the first badge test, you can come back to on the second badge test to pass whatever you did not pass the first go around. Again, if you passed all the badges, all 13 badges, get all points in this first badge test, great. You're right on track. You're probably slightly ahead of the curve. But if you pass none of them, not all is lost. You have a second chance on the second badge test and probably an opportunity on the final day as well to make up any that you didn't pass the first go around. Still, we only have a few opportunities to sit and try to take these tests, so do make the most of each opportunity to try to pass as many as you can. This badge test, like your homework, like the final, abides by our open resource policy, meaning that I don't care what resource you use to take these tests. You are welcome, if not encouraged, to bring your computer, largely because it contains your textbook, which is a wealth of information. It contains our old problem sets and the solutions, which is a wealth of information. It contains our slides and your notes, which is important. It also has access to the internet, which is a big tool that chemists use all the time. The only thing that you're not allowed to do is you're not allowed to text or message, no active live communication with a living, breathing human person, since that will ultimately test how good they are at chemistry and not you. You are welcome to use whatever fancy ChatGPT AI thing that you like. I've taught this course many times before, and I've seen many people become very reliant on the answers spat out by a computer. And I can guarantee if that is your strategy, it is neither fast nor accurate. It's a very slow way to answer these questions, and you will not complete everything, even within 4 hours. And you will not get correct, accurate answers from something like ChatGPT. So use it at your own peril, but if you would like to use it, you're welcome to use it as well. This is, again, being sort of a different format. Is something that you'll just have to see what it's like. It will be in some ways similar to a normal midterm, some ways different, all intended to be more forgiving, more gentle than a normal midterm would be. So I would try to ease any anxiety or apprehension you might have. With that, that's all we have for today. I have lab reports and problem sets graded that I would suggest you come to pick up, because it's a great way to practice and to prepare for this badge test, which will be next week, Monday. I'll hang around for questions as long as is desired, but otherwise I will see you all on Wednesday for our lab.